Greetings and again warm welcomes to the third lesson on forces and motion for the Year 12 portion of the course. So it's looking at the Stats and Mechanics book, Chapter 10, Forces and Motion. So we've done Chapter 9, Chapter 11 still to come. So we're going to think about how we can further model forces and motion, both using vectors and applying the idea of F equals ma, which is Newton's second law. So we'll look at that in a moment. But before we get going properly, let's have a look at some warm-up questions to get us in the mood. So there's 4 to have a go at here. 1, 2, 3, 4, obviously. So have a go at these independently, trying your best on your own, and then press pause and only press play when you're ready to see how you've done versus my solutions. So you can try and see how to correct yourselves independently if possible. Okay, so without hanging around any further, let's have a look at question 1 and see how we've gone on with that one. So, question 1. We're told a particle accelerates from rest at a constant rate along a smooth horizontal surface. After 3 seconds, the particle's travelled 1.8 meters. Find the acceleration of the particle. Now, the key thing here, as ever, is if we're told it's an acceleration and it's at a constant rate, we can use the SUVAT formulae. Okay, so let's just write down SUVAT and fill in what we know. So we're told the time frame is 3 seconds. Okay, so the time is 3 seconds. We're also told the displacement after 3 seconds is 1.8 meters. So we can fill in that the displacement is 1.8 meters. Subtly, although not obviously, we're told the starting velocity of a particle. We're told that it starts from rest. So that means the initial velocity, u, is 0. We want to find the acceleration of a particle, which is a, so that's what we want to find out. The final velocity, v, we're not told, we don't want to know, we don't need to know it, so I'm going to put a cross through v. So it comes down to thinking now about what formula we know that doesn't involve v, isn't relying on v, that can tell us a. And so this is in the formula book, by the way, for the A level, but hopefully with enough practice you'll spot and think that it might well be, and it is, S equals ut plus a half at squared. So now what we can do is just fill in what we know and then rearrange. Okay, so S is 1.8. U is 0, so ut is 0. So we're just going to have half multiplied by A, which we're trying to find, then multiplied by 3 squared. So it won't be long until we've found out what we need. So S is 1.8. A, like I say, is what we're trying to find out. So what we could do here is multiply both sides by 2 to get rid of this half. So 3.6 equals A times 3 times 3. 3 squared is 9, so 3.6 equals 9A. If we divide both sides by 9, therefore, we see that A must equal 0.4 meters per second squared. So let's now have a look at question 2. Question 2, we have a diagram. We've got 4 different forces acting on this object, which is modelled as a rectangular object. And so we're told here that the object is in equilibrium. Okay, because it's in equilibrium, that means the sum of the forces in any and all directions is equal to 0. Okay, so because it's in equilibrium, we can say that with absolute confidence. So therefore, the sum of forces is equal to 0. So let's just consider the vertical direction first of all. Because the sum of forces in any direction will be 0, they'll balance in any and all directions, then there's going to be no net vertical force acting on this object. And so the upwards force, R, must balance exactly against this 49 force. Okay, so R, therefore, must be 49 newtons. In other words, we're just saying that R balances out and cancels out exactly with the 49 newtons going down. 49 up, 49 down gives a net force of 0, which is what we need because we're told that it's in equilibrium. In the same way, we've done up and down there. If we just think about left and right forces, we can see that we've got 10 pushing to the left, therefore the force pushing to the right must also be equal to 10 to balance out and cancel the 10. In other words, X must have to be 10 newtons. Question 3. Question 3 very similar to question 2, however we're told here that now this object is actually accelerating horizontally to the left due to a resultant force of 12 newtons. So what's happening here is it's going to the left, so the acceleration is in this direction, and it's due to a resultant force of 12 newtons. So if it's accelerating to the left, that means the resultant force is to the left and to the left only. And so it's not accelerating up or down, it's not accelerating vertically, therefore the sum of vertical forces must equal 0. So in other words, thinking vertically, 196 must equal W. In other words, W must equal 196 newtons. It's not going up or down, so W must balance exactly with this 196. They're equal and opposite, so the forces vertically cancel. However, we're told the object's accelerating horizontally to the left. So what we can do now is use the idea of F equals ma, if we needed to. Here though, we're not told the mass, so that's not an issue. We are told the resultant force is 12. So going this way, the resultant force must be 12 in this left direction. And so the total of the forces going to the left, we've got 17. Acting against the forces to the left, in other words, what's going to the right is y. So y is working against the acceleration, so 17 minus y will give us the net force going to the left. So to the left, that way, the overall force will be given by 17 minus y. And we're told that it's 12. So 17 minus y must equal 12. With a very simple rearrangement, we can therefore see that y on this side must be equal to 5. And that, as a double check, does give a resultant force of 12 to the left. 17 take 5 ends up being overall 12 to the left. Finally, we can have a look at question 4. So question 4, we have to use the factor theorem to show that x minus 2 is a factor of this expression here. So we need to remember what the factor theorem does. So what we do here is, if we know that x minus 2 is a factor, then f of 2 must be a root. So if we can prove and show that f of 2 equals 0, that shows us that x minus 2 is a factor. So let's just try f of 2. So all we're doing right now is inputting 2 for x and seeing what this expression is going to be equal to. So f of 2, that's going to be 2 cubed minus 4 lots of 2 squared. Don't know if I put cubed, that's just me being a bit silly. Plus 11 lots of 2 minus 14. So 2 cubed is 8, 2 times 2 times 2. 2 squared is 4, so 4 times 4 is 16, so we're subtracting 16. 11 times 2 is 22, then minus 14. So if we just calculate this, 8 takes 16 is minus 8, plus 22 is 14, then 14 minus 14 is 0. So f of 2 equals 0. Therefore, what that tells us is that x minus 2 is a factor of this expression, x cubed minus 4x squared plus 11x minus 14. Now for part B, slightly more complicated, we now need to show that x equals 2 must be the only real solution to this equation here. We found a factor, so x minus 2 is a factor, so what we now know is that we should be able to divide this expression here by x minus 2, and we should end up with a 0 remainder. So if we take this here and divide it by x minus 2, we know quite confidently that the remainder is going to be 0. So let's just do this carefully and see what we get for the quotient. So first off, divide x cubed by x. What we get here is x squared. Now we multiply this x squared by the x minus 2. So x squared multiplied by x minus 2, that gives us x cubed minus 2x squared. Now we subtract. X cubed takes x cubed, that always is going to cancel. Next here though, we've got minus 4x squared minus 2x squared, which means minus 4x squared plus 2x squared, which leaves us with overall minus 2x squared. And before we forget, what we always need to do, if there's something above to bring down, we bring it down. So it's plus 11x, we bring down to our current line, and then we go again. So now we're going to divide minus 2x squared by x. So minus 2x squared divided by x, that's just going to give us minus 2x. After dividing, we multiply, so minus 2x times x minus 2, minus 2x times x gives us minus 2x squared, then minus 2x multiplied by minus 2, minus multiplied by minus gives us a plus, so we're going to have plus 4x. After multiplying, we subtract. So minus 2x squared minus minus 2x squared means minus 2x squared plus 2x squared. This cancels, as it always will do. Over here, 11x subtract 4x, that's going to leave us with 7x's. And again, we need to bring down the next term from above. So bring down the minus 14 here to join the current line. We've now brought down everything from above, so we know that this next iteration of the algorithm is going to be the last cycle we have to do. So finally, 7x divided by x. 7x divided by x, that just gives us plus 7. Next, we multiply. So 7 multiplied by x minus 2. 7 times x is 7x. And then we've got here, oops, it's not quite working. I think the computer's going a bit slow. Computer must be tired. So 7 times x is, oops, 7x. And 7 multiplied by minus 2 is minus 14. And as you would probably guess, if you're used to polynomial division, we knew that x minus 2 was a factor, so we'd anticipate this would have no remainder, which of course it doesn't. So this cancels perfectly to leave us with 0 remainder. And so now what we can say from all of this is therefore x cubed minus 4x squared plus 11x minus 14 equals the divisor, which is x minus 2, multiplied by the quotient, which in plain English is sort of like our answer, which is this. So we get x squared minus 2x plus 7. So if we read the question and just contemplate it briefly, we have to show here that x equals 2 is the only real solution. So in other words, we have a solution of x equals 2 from this green bracket. We need to prove that this blue bracket is going to yield no real solutions. Now at this stage we need to recall what property of a quadratic tells us how many solutions it has or does not have. And that property is the discriminant. So what we need to do is calculate the discriminant for x squared minus 2x plus 7. So triangle just means discriminant. I didn't need to write it like this. You could have wrote it differently, just put triangle or wrote discriminant of this, and that would have been fine. So the discriminant is b squared minus 4ac. So b squared is the minus 2 by the minus 4 times a times c. So a is the coefficient of the x squared. We've just got a 1x squared, so that's just going to be a 1. Then we multiply by c, and c is just simply the constant term, which is a 7. Then we see what this equals. So minus 2 times minus 2 all squared is 4. But minus 4 times 1 times 7, that means minus 28. 4 take 28 is minus 24. Doesn't particularly matter what it equals. The only thing that really matters is that this value here is less than 0. So therefore, only one solution. Only one solution, and that's when x equals 2. In other words, if you wanted to carry on and just bore the examiner with a bit more detail, in other words, i.e., no solutions from x squared minus 2x plus 7, because we've just done the discriminant test on that and shown that the discriminant is negative, therefore 0 solutions from this quadratic factor. The only solution, therefore, is this linear factor here, x equals 2. Let's now have a look and think about the main body of the lesson. So, we're going to talk about forces and acceleration right now. So, a non-zero resultant force that acts on a particle will cause the particle to accelerate in the direction of the resultant force. Newton's second law states that the force needed to accelerate a particle is equal to the product of the mass of that particle and the acceleration produced. So it's essentially the result when you multiply the mass by its acceleration. So in plain English, the equation of motion for the particle is the overall resultant force, F, equals the mass of a particle multiplied by the acceleration of the particle. It's quoted simply as F equals ma. So how does this link to gravity, which is one of the most serious forces? Little joke there. I won't explain it any further. It's a terrible joke anyway. So gravity, how does this relate to gravity? Well, the force due to gravity acting on an object or any object is called the weight of the object, and it always acts vertically downwards towards the centre of the Earth. So earlier in the course, chapter 9, I mentioned this briefly, we worked out that a body falling freely under gravity experiences an acceleration g, so g stands for acceleration due to gravity, and on the surface of the Earth that's approximately 9.8 meters per second squared. However, what we can do here is use the relationship F equals ma and consider the simple model of having no air resistance. We can write the weight W of an object of mass m kilograms in terms of g. So what I mean by this is just imagine an object of mass m falling down to Earth. So the only force acting, if it's got no air resistance, is the force due to gravity, which is called, quite simply, its weight. So if any force acting, if we consider there to be no air resistance, is W. Now we can quote F equals ma. Okay, so the resultant force acting on the object is equal to ma. With no air resistance, the force acting is just for weight. So the weight is going to be equal to the mass of the object multiplied by the acceleration of the object. However, if any force acting we're considering is for weight, then the acceleration will be the acceleration due to gravity, which is g. So this acceleration is one and the same as g. And so what we can rewrite the weight as in mechanics is that the weight of the object is the same as the product of the mass of the object multiplied by the gravitational field strength, which on planet Earth is 9.8 meters per second squared. And so W and mg are interchangeable. So often we'll use mg in place of the weight of the object. We mentioned this in chapter 9, but I'm mentioning it here again. W equals mg. Let's now consider some worked examples applying Newton's second law, F equals ma. So we've got parts A and B for question 1 here. So in both diagrams, the body is accelerating in the direction indicated by these double-headed arrows. So we can just label this in clearly now. So it's accelerating for part A in this direction, for part B to the left. So what we need to do here is to find the magnitudes of the unknown forces x and y. So the main thing to notice here is in both A and B, the object accelerating purely in the horizontal direction. There's no up or down component to it. So what we can say here then for A and for B is that the total of the forces going up and down is 0. This is just my sort of shorthand notation. The sum of the forces in the vertical direction is 0, because the object isn't going up or down at all. It's accelerating purely to the side, not up or down in any way. So based on that, we now can sort of work out that y must be the same as 2g. So for part A, y must equal 2g. And using that g is 9.8 meters per second, we can calculate a numerical value for what y is. So y is 2 times 9.8, which we can do easily enough on the calculator. So 2 times 9.8, that's going to come out to be 19.6. So y is 19.6 newtons. We'll do that in a black colour, not red. So 19.6. Now going to the right hand side, we can apply F equals ma. So F is the resultant force going to the right. So the force going to the right, in this positive right direction, it's x, but holding it back, working opposite to the acceleration is 4. So we're going to subtract 4. So the resultant force in the direction of the acceleration, which is 2, is x minus 4. So the resultant force in the direction of acceleration is x minus 4. And that's going to equal the mass of the object, which is 2, multiplied by its acceleration, which again is 2. So in terms of filling in these numbers, the values, m is 2, so we can just say that m here is 2 kilograms. So if we simplify, we get that x minus 4 equals 2 times 2, which is obviously 4. So therefore, x must equal 8 newtons. We can now apply similar ideas to part B. So again, for part B, there is no up or down acceleration. So the resultant force in the vertical direction is 0. So we can use the same idea for part B. So the sum of the forces in any up and down direction is equal to 0. So the upwards forces, which in this case is y, must be equal and opposite to the forces pushing down. So y going up must equal 20 plus 4g, which are going down. And again, because we know what g is 9.8 meters per second squared, we can calculate what this is using the calculator. So y must be 20 plus 4g, which means 4 times 9.8. So y is 59.2 newtons. What we can do now is work out the forces going to the left or right. So the object is accelerating to the left. It's going 2 meters per second squared, acceleration to the left. So again, we can apply the idea of F equals ma to this particle or object. So the resultant force going to the left, this F, which means resultant force, well, the force going in the direction of acceleration is 80, but holding it back, working against this force, is x. So the overall force going to the left is 80, knock off the x, so 80 minus x. That's going to equal the mass of the object, which is 4, multiplied by the acceleration of the object, which is 2. So again, just using F equals ma, this time the mass of the object is 4, and the acceleration, again, same size as the acceleration part A, just a different direction, acceleration is 2. So we can just simplify this and it'll drop out nicely. So 80 minus x equals 4 times 2, 4 times 2 is 8. So therefore x is going to be 80 subtract 8, which is 72 newtons. So that's what x is. So that's question 1 done. So let's now have a look at the next one, question 2. So a scientist calculates that a human being weighing 868 newtons on Earth would weigh 623 newtons on the planet Venus. So we need to use this information to work out the acceleration due to gravity on Venus. Well, using what we worked out before and mentioned before, the weight on Earth equals the mass of the object on Earth. Well, mass is constant. Mass is invariant depending where you are in the universe. Mass is simply a measure of how much stuff is inside an object. So mass, typically speaking, doesn't change from one situation to another, but its weight may. So the weight on Earth is the mass multiplied by the gravitational field strength, g, on Earth. So we're told here what the weight on Earth is. It's 686. So 686 equals the mass on Earth, whatever that might be, multiplied by g on Earth, which we know, or should know, if we've committed it to memory, g on Earth to 2 sig figs is 9.8. We can therefore work out the mass of the object by just a simple rearrangement. So the mass is going to be 686 divided by 9.8. So if we just take the calculator and work this out, 686 divided by 9.8, that gives us 70 kilograms exactly. So the mass of this object is 70 kilograms. We can then use this and apply F equals ma to the situation on Venus. So the weight on Venus will be the mass on Venus, which is just m, because m is invariant, depending on which planet you're on. The mass is the mass is the mass, multiplied by the g, gravitational field strength on Venus. So g subscript Venus, that's just my shorthand for saying what is the acceleration due to gravity on Venus. So if we just plug in what we know, the weight on Venus, we're told, is 623. So 623 equals the mass of the object, which we worked out was 70, multiplied by the gravitational field strength on Venus. So therefore, the gravitational field strength on Venus, the acceleration due to gravity on Venus, it's one and the same thing. It's going to be 623 divided by 70. So if we work this out now and round it to an appropriate degree of accuracy, I would say we could round it to either 2 or 3 significant figures if we feel generous. So 623 divided by 70, we get here, well, it comes out at 8.9 anyway, so 8.9 meters per second squared. So very similar to that of Earth. For that reason, Venus is often informally considered a sister planet to Earth. It's not really, because you can't really live on Venus, it'd be incredibly toxic, you'd not last very long on it at all, especially because it's gas. But in many ways, in terms of the size of it and G, it does have many similarities in some ways with Earth. So the gravitational field strength on Venus is 8.9 meters per second squared, which is very similar, I suppose, to our 9.8 meters per second here. Final question now. Final worked example, question 3. We have a body of mass 6 kilograms, which is being pulled along a rough horizontal surface by a horizontal force of 22 newtons against a constant frictional force of 4. So we're told that the body is initially at rest. We need to find the acceleration of this body. So we've got a surface, we've got friction. What I'd suggest doing for this situation is just doing a little diagram. So it's horizontal, so let's just draw in a flat surface. Now what we need to do, or what I'd suggest we do, is to draw the object in, like so, place it on the surface, and model and label the forces acting. So it's being pulled along by a force of 22 newtons. So first thing we're going to do is label on the diagram a force of 22 newtons. There's also a constant frictional force, so constant means it's unchanging, and that's a force of 4 newtons. So friction will act between the surface and the object itself, so the friction is going to be acting essentially opposing the motion. So the friction is going to be acting the opposite way, so it's going to be going this way. Mess it up, something fierce. Let's swizzle this around like so. I'll make the line slightly thicker too. Maybe not. Okay, so the force of friction is acting this way, and I'm going to call this 4 newtons, because it says here in the question it's 4 newtons. As well though, it has a mass of 6 kilograms. So if an object has a mass and it's within a gravitational field, in other words it's on the Earth, it will have a weight associated with it. So we need to label on the weight of this object. So for weight, we'll be acting straight downwards towards the centre of the Earth. If its mass is 6 kilograms, what we can do, we can label the weight as 6g newtons. Again, now this makes much more importance in year 13. If you notice here, forces must balance horizontally. It's being pulled along a horizontal surface, so it's going either left or right. It's not falling through the floor, it's not floating up. And so the forces going up and down must balance, and so what this means is there will be an equal and opposite reaction between the surface and the object that holds the object up in its place so it doesn't fall through the floor. Now this is differently labelled from question to question as either N or R. I'm going to label it N. N stands for normal reaction force. Okay, so I'll just mention that here, should you forget. So N means normal reaction force. Now you might be thinking, what's normal about it? You know, is it not abnormal? Normal as in, what do you mean by normal, sir? Well, normal just means perpendicular. So normal is a different word that physicists generally, some mathematicians too, use for perpendicular. So normal means it's perpendicular to the surface. So the normal reaction will be acting at 90 degrees to the surface it's in contact with. And so N will equal 6g. The forces up and down will cancel, so the object is in a vertical equilibrium. So now we can go forward and work out the question. So work out A, the acceleration of a body. So what we can do here is apply Newton's second law, F equals ma. So the acceleration is going to be in the direction of the resultant force. So N, like I've said here, N is going to equal 6g. It's going to be equal and opposite to its weight. The acceleration is going to be acting in the direction which the object's being pulled. 22 newtons is greater than 4, so the 22 newton force will win, if you like. It's going to end up accelerating in this direction. So we can just do a little diagram, a little arrow here to say it's going to be accelerating this way. So F equals ma. The overall force to the right is the 22 newtons, which is already going to the right hand side. Subtract this 4 going against it. So 22 minus 4 equals the mass of the object, which is 6 kilograms, multiplied by the acceleration of the object. So let's just simplify now. 22 minus 4, that's 18. 6 times a is 6a. So therefore, the acceleration will be 18 divided by 6. The acceleration is 3 meters per second squared in this positive direction going to the right. Now part B. We're told here what the distance travelled has to be in the first 10 seconds. Well, it's been pulled along by a force of 22 newtons. We're not told that this force is changing. The force resisting it is a constant force of 4 newtons. So we need to deduce something here. We need to deduce that it's a constant resultant force, therefore constant acceleration. So constant resultant force that's going to imply a constant acceleration. And you should know by now, if the acceleration is constant, we can apply the SUVAT formulae. So that's what we're going to do here. We're going to use SUVAT and fill in what we know. So what we're told here is that the body is initially at rest. So it's initially at rest. That means its initial speed, initial velocity I should say, u, is 0. We want to know how far it travels in the first 10 seconds. 10 seconds is a measure of time, so t we're going to use is 10. We know from part A what the acceleration is. The acceleration is 3 meters per second, so we can fill in that A is 3. We want to work out the distance travelled. Distance travelled, that links to displacement, which is s. So we want to work out s, so I'm going to put a question mark next to s because we're interested in finding that out. What we're not interested in, what we don't care about, is v. So I'm going to put a cross by v. We don't know it, we don't need to know it, we don't care. So which of the SUVAT formulae does not involve v, is not influenced by v? So again, it seems like it's the most common formula ever for SUVAT. It's s equals ut plus half at squared again. That formula will crop up time and time again. It seems that this one is the most favoured by examiners as well, for some strange reason. Perhaps because it's quadratic, so it's got more richness to it. I don't know. So we just plug in what we need to work out. So we need to work out s. U is 0, so ut is also 0. So we've got half times a. A from before is 3. So half times 3 times t squared, and again from the question, the time frame we've got is 10 seconds. We want to find out the distance covered the first 10 seconds, so t is 10. So s equals half times 3 times 10 squared. And if we calculate this, half times 3 is 1.5 times 10 squared, so times 100, that's going to be 15. Now, what I'd suggest you do is just use your calculator anyway. Don't be too smart about it. So half times 3 times 10 squared, that gives us 150. Of course, it does, 150. I was thinking 50 and I missed a 0, so point in fact, use your calculator. So yes, 150 meters. Now part C is almost a trick question. It's not a trick question because it is a valid question, but it's something you need to be careful about. The magnitude of the reaction between the body and the surface. Well, the reaction force, like I mentioned, it's called the normal reaction force. That's just one name for it. Sometimes it's just called R, which is the reaction force. So N must have to balance with this 6g. It's as simple as that. The reaction must be equal and opposite to the weight the floor is having to carry because of the object. If it weren't equal, either the object would fall through the floor, it would break the floor, or if it were greater than the weight, the object would be pushed up and would be either floating or be rebounding like some sort of trampoline. So it's safe to assume that N would have to balance exactly with a 6g weight of the object. So N equals 6g. Simple as. So knowing that g is 9.8, we do 6 multiplied by 9.8 and we're done. So 6 multiplied by 9.8, 58.8 newtons. and we're done. So that's all there is to it really. It's now just over to you to try some of these on your own. So on that note, here's the suggested exercises for this subchapter. So page 164, exercise 10C, try all the questions from question 4 through to question 11. And you know the drill by now. If you get stuck, ask me. If I'm not around, drop me an email, come and see me after college, or perhaps even better than that, just leave a comment in the comment section on the video. So work hard, keep trying these questions, and I'll see you again soon, hopefully. Okay, so take care, and I'll see you all next lesson.